right, so if we want to figure out what the graph of this looks like, I suggested that we square both sides, keeping track of the fact that because z was defined as the principal square root here, that means that z is bigger than or equal to 0. So we're getting the top half of this, which is a quadric surface. Now notice, all three variables are squared, but if I were to move the z's over to this side, it would not be equal to 1. It would be equal to 0. Okay. So here, in the xz plane, z squared equals x squared, that's that degenerate hyperboloid. That's going to be intersecting lines. Same thing in the yz plane. In the xy plane, it looks like if x squared plus y squared equals 0, we're getting just a single point. But then if I'm in a plane above that, I'd be getting a circle. So it looks like we're getting the top half of a cone. In just everyday English, we might refer to this as a cone. It's actually half of an elliptic cone, or in this case, it's actually a circular cone. Okay. So there's the graph of that. Excellent. Now, when we're working with functions of two variables, the graph is in 3 space. If I have a function of 3 variables, the graph would be in 4 space. Let's just say I had x squared plus y squared plus z squared. What do I call the output? We usually call it w. Okay? There's no letter that comes after z, so we just go back to the last one before x. Okay? So the output will generally be a w value. That's the variable that we will use for that 4th dimension. All right. I would like to start talking about domains of functions. Now, domains are going to be a subset of either 2 space if it's a function of 2 variables, or 3 space if it's a function of 3 variables. So as long as I'm talking about the domain, even if I have a function of 3 variables, I can think about that graphically. Okay. Once I have the domain together with the w value, now I'm in 4 space and my brain starts to hurt. But if I'm just talking about the domain, that's going to be a subset of 3 space, okay, for a function of 3 variables. For a function of 2 variables, it's just a subset of 2 space. So let's try a couple. Let's look at f of xy equals the square root of xy. What I'd like to do is describe the domain algebraically using set builder notation, and then also sketch the domain. Okay? And then we'll take a look at some examples with 3 variables as well. Okay? So here, in order to be able to take the square root, I know that x times y has to be bigger than or equal to 0. So I could simply describe the domain as being the set of all points x, y, such that that inequality is satisfied. Okay. But it's often going to be more useful to have a graphical sense of what the domain would be. So let's just take a look. Here's the xy plane. Notice the boundaries that I'm going to have are going to be the places that would make this equal 0. That would be xy would equal 0 if x equals 0 or y equals 0. So those are my 2 axes. And I do want to include them because this is an inclusive inequality. If I'm including them, I'll go ahead and draw them as solid lines. Okay. Notice those boundaries divide the plane up into 1, 2, 3, 4 regions. Once I've determined what my boundary curves are, that's going to divide, in this case 2 space, if it were a function of 3 variables, 3 space, into regions, and I just need to see which part of the region I want to keep. So, in quadrant 1, x and y are both positive. X times y would be positive. We'll keep quadrant 1. In quadrant 2, x is negative, y is positive. X, y would be negative. No points in quadrant 2. In quadrant 3, x and y are both negative, so their product will be positive. And in quadrant 4, x is positive, but y is negative, so their product is negative. So basically what we're getting is quadrants 1 and 3, including the axes. Now, compare that to g of xy, which is the natural log of xy. There, I would need xy to be strictly bigger than 0 in order to evaluate the log. So my domain would be the set of all points xy such that xy is strictly bigger than 0. Now, if I were graphing that, the convention in 2-space is if the boundary is not included, draw it as a dotted line. So I would draw my axes as dotted lines and then shade quadrants 1 and 3. So very similar, but not quite the same. Okay, let's try one that's a function of 3 variables. Let's say f of x, y, z is the square, no, let's not do the square root. Let's do the natural log of x squared plus y squared minus z squared. Okay, excellent. So, this is a formula for my w values, but if we're talking about the domain, we're looking at a subset of 3-space. We're looking at the points x, y, z for which this is defined. So I can say my domain is just the set of all points x, y, z such that x squared plus y squared minus z squared is strictly bigger than 0. Okay. So my boundary, and it's going to be a boundary surface in this case, would be the set of all points where x squared plus y squared minus z squared is equal to 0. And that boundary is not included because it's a strict inequality. Now, when we're in 3-space, we will not have the convention that if the boundary isn't included, we draw it as dotted lines. That's because I already draw dotted lines to indicate that something is behind something else. Okay? And so if I had, if I look at this, I can recognize that's just my circular cone all over again. So usually I would draw it something like so. I wouldn't want to mean that this is included but this isn't. I'm using a dotted line here to indicate that that's not included. Now, because none of this boundary is included, if I wanted to, I could draw the whole thing with dotted lines. But then I sort of lose the ability to say that the dotted line there is because it's not included. So generally what we'll do is we'll just draw the surface as we normally would and use words to say the boundary surface is not included. We have a nice visual way that works in 2-space. That does not generalize to 3-space. Okay. So that's my boundary surface. Now I need to figure out which part of 3-space do I want. I want the places where this is bigger than 0. So is that going to be the points inside the cone or outside the cone? Let's see. Okay. Well, probably what's easiest to do is just to sort of pick some test points. So if I take a look at a point right here, x and y would be 0, but z would be, let's say, 1. Okay. 0 minus 1 is not bigger than 0. The inside of the top half of the cone is not included. Below, I would get the same thing. If x and y are 0 and z is negative 1, I would get something negative. So what I want is the outside of the cone. Okay. Now, that's a little bit misleading because it almost looks like there's nothing that's directly in front of the of the z-axis here. But there is, because if the cone only sticks out so far, the space in front of that cone is included. So you may very well need to supplement your picture with words and just say everything outside of the cone. That's suggested by this picture, but there is stuff in front of the cone and there's stuff behind the cone as well. Another thing that you can do, although I can't really do it with whiteboard markers, is if you have a pencil, you could shade the cone really solidly and then lightly shade around it. That way you can sort of see that you are shading in front of the cone. It's just that there's something really darkly shaded behind it. So you've got several options, but feel free to supplement your pictures with words. Sometimes that is necessary in 3-space.